Good morning, everyone. This morning I will present to you my topic by taking this value. By the way, I am Juvy Mariana Zante, Bachelor in Secondary Education, majoring in Science. My topic is spring. So we will talk about spring and how spring exists in universe and how it applies in physics. So let's start. Spring is an object that can be deformed by a force and then return to its original shape after the force is removed. Spring come from a huge variety of different forms, but the simple metal coil spring is probably the most familiar. Springs are an essential part of almost all moderately complex mechanical devices, from ballpoint pens to racing car engines. There is nothing particularly magical about the shape of coil spring that make it behave like a spring. The springiness, or more correctly, the elasticity, is fundamental property of the wire that the spring is made from. A long, straight metal wire also can be spring back following stretching or twisting. Winding the wire into spring just allow exploit the properties of a long piece of wire in a small space. This is much more convenient for building mechanical devices. The response of metal wire to stretching or axial load and twisting or torsion is governed by different physics, and the design of a particular spring can exploit one kind of deformation over another. In addition, the elastic properties of metals depend strongly on their grain microstructure. This can be changed by stress and control heating, cooling process known as annealing. If a metal wire was formed from a straight section into a coil, then it is likely that it will need to be re-annealed to restore its original elastic properties. What happens when a material is deformed? When a force is placed on a material, the material stretches or compresses in response to the force. We are all familiar with the material like rubber, which is stretched very easily. In mechanics, the force applied per unit area is what is important, that is called the stress symbol. The extent of the stretching or compression produced as the material responds to stress is called the strain symbol, or epsilon. Strain is measured by the ratio of the difference in length delta L, the original length or local orbital, along the direction of the stress, or epsilon is equals to delta L, or local orbital. For most materials, the strain experience when small stress is applied depend on the tightness of the chemical bond within the material. The stiffness of the material is directly related to the chemical structure of the material and the type of chemical bonds present. So, what happens when the stress is removed depends on how far the atoms have been moved. There are broadly two types of deformation. First is elastic deformation. When the stress is removed, the material returns to the dimension it had before the load was applied. The deformation is reversible and non-permanent. Second, elastic deformation. This occurs when a large stress is applied to a material. The stress is so large that when removed, that the material does not spring back to its previous dimension. There is permanent, irreversible deformation. The minimal value of the stress which produces plastic deformation is known as the elastic limit for the material. Any spring should be designed and specified such that it only never experiences elastic deformation when built into a machine under normal operation. Now, let's proceed with the calculation that we will use the Hooke's law. The Hooke's law say the restoring force required to compress or stretch the spring it is proportional to the distance of the string is deformed. The formula form of Hooke's law is F is equals to negative K delta X. The F is served for restoring force of the spring, and this K is proportionality constant called the spring constant, and for this delta X is to change the spring position due to the deformation. The minus sign here is show that the restoring force is the opposite of the deforming force that spring tries to restore itself to its unreformed state, that the spring pulls back against the compression. We're pulling down on the spring will cause an extension of the spring downward, which will in turn result in upward force due to the spring reaction. It is always important to make sure that the direction of the restoring force is specified consistently. When approaching mechanics problem involving elasticity, for example problem, we can often interpret the extension of X. First-dimensional vector in this case, the resulting force will also be a first-dimensional vector, and the negative sign in the Hooke's law here is give the correct direction of the force. Then, when we calculate the X, it is important to remember that the spring itself will also have some nominal length or the local orbital. The total length of the spring under extension is equal to nominal length plus the extension. So it will be the L is equals to LO minus X, plus X rather. And for the spring under compression, it will be the L equals to LO minus X. I have here sample problem for your additional understanding. The question is, how much force is needed to pull a spring with a spring constant of 20 newtons per meter at a distance of 25 centimeters? So the key of the spring is 20 Nm. Then the delta is 25 centimeter. But the 25 centimeter is converted to meter, so it will become a 0.25 meter. Now, it will plug these values into the Hooke's law formula, since we're looking for the force required to pull the spring apart. So we don't need the minus sign. So we already wala na siya sign na negative. So the formula is the F is equals to negative X delta X. But since we are looking for the force to pull the spring, like what I said before, we don't need the minus sign. So we need to erase the negative, that it could be F is equals to K delta X. So K here is for 20 Nm subtracted to 0.25 meter. So we crush out the meter here, meter. So then we subtract it. So the result is F is equals to 5 Newton. The force of the 5 Newton is needed to pull this spring distance of 25 centimeters. Now let's proceed with the spring with mass. So what is the extension of the spring in each case, as you see on the picture? Okay, as you can see in the picture, in this figure, the spring is pulled in the same mass, which is 1 kilogram, both horizontal and vertical. Since the force pulled the spring in the same magnitude, we will assume that extension is also the same in both cases. The complication here is that the spring has a mass, while in the vertical cases, the force of the gravity acts on the spring in the same direction, the force due to the mass. So the mass of the spring adds to the weight that extend the spring is supporting a total of a 1.05 kilogram, which causes an extension of 1.05 kilogram by 9.81 metric system. So it divided by into 200 Newton per meter, which is spring constant. So that the result is 51.5 meter. So all asking where it come from the this 9.81 rather metric system. It is the Newton law formula that stated that kilogram is multiplied by 9.81 to get the measurement. In the horizontal case, the pulley has changed the direction of the force. The force due to the 1 kilogram weight acting on the spring is now orthogonal to the force of the gravity acting on the spring. So, the extension of the spring is supporting only 1 kilogram. 1 kilogram. Okay. Therefore, the extent of 1 kilogram by 9.81 metric system is divided by into 200 is equals to 49 millimeter. Is equals to 49 millimeter. This difference can be quite significant, and if it's not taken into account, that can lead an incorrect result in the laboratories. In physics, teaching laboratories, we often use spring balances to measure the force. So, for a spring balance, is simply a spring with a pointer attached and a scale from which the force can be read. Because the manufacturer of the spring is balanced, they expect their product to be used. Critically, it is the example is the fisherman measuring the mass of the fish, or the scale is the calibrated to take into account. So the mass of the string and the hawk, or ganyan niya, the hawk that it will give the incorrect solution, absolute result, if to measure the horizontal force. However, Hawk's law tells us that there is a linear relationship between force and extension. So, because of this, we can still rely the the scale of the relative measurements when we use the horizontal direction. So some spring balance have an adjustment screw that allow the 0 point to be calibrated, or eliminating this problem. So that's all for my report. Have a good day. Monday.